In this video, we're going to review how to solve homogeneous differential equations. In differential equations, the term homogeneous has two different meanings. And you may remember one, like when you have a differential equation, on the right side, there's no formula. There's no function, like it's just equal to zero. That's normally what we call homogeneous. But here, that's not the meaning. It's a different meaning. So let's talk about what we really mean by homogeneous equation in this sense. So we say a differential equation is homogeneous if it can be written in this special form. That means in the normal form has this format. So it's a right side is simply a function of y over x. And then what we do, so if you can write it like that, we call it a homogeneous differential equations. And then what we do, we're going to make a substitution for this term. We just call this term is um, v, so we'll call it like that. So and then we solve this as a regular substitution problem. But before we do that, we would like let's look at some examples where we can figure out whether whether they are homogeneous or not. So let's look at a couple of examples. So as the first one, let's look at this one. Dy by dx equal x plus y over x. And then you can see that what we can do, we can divide this term by terms. You can write this one as x of x plus y of x, and then first one is going to give you 1, the second one is y over x. So you see that you can write it as a function of y over x. So yes, so it is a homogeneous one. So let's look at the next one. So we have x plus y over y now. So what we can do, again we can divide the top and bottom by x. So when you do that, you can see you're going to get 1, and this one going to be y over x, and the bottom also going to be y over x. So what we did, we divide the top and bottom by x term, and then now you can see it is clearly a function of y over x. So you can see we have y over x, no other terms. So yes, and then let's look at the next one. Say we have x squared dy by dx equal y squared minus 3xy. So we do the same thing. We're going to divide. We're going to try to bring it to the normal form by dividing by this term. So we can write this one as dy over dx. If you divide, you get y squared minus 3xy over x squared. And then as we did before, we can do that. But there is like another way to see this is this is in homogeneous form. The other technique is you can check the degree of each term, and you can see each term has degree 2. The first one has a degree 2, second one also has a degree 2, and the bottom also has the degree 2. So that's the other way to see. So if you see that all those terms have the same degree, you can write it as a homogeneous one. So check whether they have the exact same degree for all the terms. Okay, so now we do the normal way. So we start dividing by x squared. We can write it like that. And minus, we have 3xy over x squared. And you can see the first one is clearly, you can write as y of x, whole thing squared, the first term. In the next term, you can see, you can first cancel one of the x terms, and then you get 3, and then you have y over x. So yes, so we can do that. So you can see it is a function of y over x, so it is homogeneous. So let's look at the next one. Suppose we have dy by dx equal x e to the y over x divided by x minus y. And again, in this one, what we can do, we can divide the top and bottom by x. So if we do that, you get e to the y over x in the numerator. In the denominator, when you divide, you get 1 minus y over x. And you can clearly see that it is a function of y over x. So even though it doesn't look like, this is a homogeneous equation. So let's look at the next one. So next we have dy by dx equal x minus y over x cube plus y cube. And you can clearly see that the degree of the numerator is 1, and the degree of the denominator is 3. They don't match, so it cannot be. You cannot write this one as a homogeneous equation. You can try. So degree of the numerator does not equal degree of the denominator. For each term, you have to check every term should have the exact same one. So let's look at that in the next one. So we have x minus y plus 1 over x plus y. And as polynomials, the top one has a degree 1, bottom one has a degree 1. But that's not what we are talking about. Here the degree has to be the same for each term. So here there's a 1. That 1 create a problem because it's a degree 0. So that means, so this is not of homogeneous because the two different, some terms doesn't have the same degree. Okay, so let's look at the last one. Say we have ln y minus ln x divided by 1 plus e to the yx, and you know that from the logarithm properties, when you have a subtraction, it is a division inside. So we can write this one as log y over x and divided by 1 plus e y over x, and you can clearly see that is a function of y over x. So this is a homogeneous equation, even though it looks little difficult. Okay, now let's try to see how we can solve these kind of problems. Now let's talk about how to solve the homogeneous equation. So different book use a different technique. So here we discuss a technique that can be done quickly. So we start with the equation. So we know that any homogeneous equation can be written as a function of y over x. And let's call this equation star. Now the idea is we're gonna pick that yx as v. So this is the main substitution we use. And then what we do after that, we treat this one as a regular substitution problem. If this is the case, then you can actually write this one as y equal vx. And what we do after that, we just take the derivatives. So we take the derivative and then using the chain rule, we can write it like this. So taking derivatives and using the product rule, so you can write it like this. So that means first term is going to be y prime. On the other side, we use the product rule. So that means we get v plus v prime x. So that is the formula that we use. So this is always the same because it's the same formula. Now what we can do, we can substitute this into the two sides. For the derivative side, we can substitute the second one. For the right side, we can substitute v equal y over x. So by substituting, we get on the left side we get v plus v prime x. On the other side you get a function of v. So that's the idea, and then you can see once you do that, it is going to be one of those forms. So it can be separable or it can be first order linear, and we're just going to solve this one now. So most of the time it's going to be separable. After that, what we can do, we're going to solve this equation first for v. So solve for v first, and after we solve for v, then we use the y equal vx substitution to solve for y. So we just need to multiply by x, the v solution, and then you get the solution y. So let's see how it's going to work. So let's look at a couple of examples now. Solve the following differential equations. So look at the first one. Suppose we have dy by dx x plus y over x. That's the first example we discuss when we talk about the type. And we discussed that we can write this one as by dividing by x, the two terms, you can write this one as 1 plus y over x. And then what we do, we're going to pick this one as v and then use the substitution. So let's do that. So let v equal y over x. And this is going to give you, if you cross multiply y equal vx and then take in derivatives, we get as before y prime equal v plus v prime x. You can just use it like that. Okay, now what we can do, we can substitute this one into the equation. We get v plus v prime x on the left side, and on the right side you can see it is 1 plus v. And you can see sometimes, you know, you can actually simplify. See, you can get v get cancelled out completely. So now we can write v prime as dv by dx. So we can write that again. So it's dv by dx times x equal 1. And you can see this is a separable equation. So you can separate and integrate. So let's do that now. After separating, you can write this one as dv, and on this side 1 over x dx. And then we integrate both sides separately. And on the left side, we get v On the right side, which is the natural log, so it's the ln absolute value of x plus c. And then what we can do, we're going to substitute. So since v equal y over x, we can write y over x equal ln x plus c, and then we're going to multiply by y, so y equal x ln x plus cx. So that is the general solution for this problem. And if you know the initial conditions, then we can use them to find c. So that's how you solve a problem using the how you solve a homogeneous equation using the v equal y over x substitution. So let's look at one more problem. So we have x cubed dy over dx equal 4y cubed plus x squared y, and you can clearly see that each term has the same degree. So by the alternative definition, this is homogeneous. Now dividing by x squared, we can write x cubed actually. We can write dy over dx on this side. We always write the normal form. And so we can write this one as 4 y over x cube, and if you divide by x cube, you're gonna get y over x, and you can see it is all the it's a function of y over x. So we're gonna use a substitution. This gives you, and then we're gonna substitute, and we get v plus v prime x on the left side. On the right side is 4 v cube plus v, and again you can see the v term get cancelled out, otherwise it would be very difficult actually in this case. And then you can see that whatever we have is a separable equation, so we can separate the rest. So when you separate the terms, we get this one, because we can write v prime is dv over dx, so that's how we write, and then we can integrate both sides, and you can see this is easy to integrate. So when you integrate on the right side, you're gonna get 4 ln absolute x plus c, which actually you can write, if you bring the 4 inside, you can write this one as ln x to the 4th power plus c. You do not need absolute anymore because it's always positive or 0, so we don't need that. And the left side, what we can do is we know that v to the 4 you can write as v to the negative 3. That means when you integrate, you're going to get negative 1 over 2v squared. Okay, so we can substitute that. So that means we can write the answer now as negative 1 over 2v squared equal, on the other side we have ln x to the 4 plus c. So that means we solve for v now. So we just need a little bit of algebra, but we almost done. So let's do that part. So next what we do to cancel the fraction, we're going to multiply by negative 2 both sides. So we can write this one as 1 over v squared. When you multiply negative 2, you get negative 2 ln x to the 4 negative 2 c. We can say c1 for some reason. Okay, and then what we can do, we can bring this one over there as a power. So when you do that, so you can write this one as ln so we leave the negative sign and bring the 2 in, so it's going to be ln, you multiply the powers, so you can ln 8, because power for power, when you have two powers, what happens, they multiply each other. So we have x m n going to be x m times n. Okay, and then for the other term, we can call this whole term is c for simplicity. So we can write this one as c, just to make the algebra easy. Okay, and then what we do, we're gonna flip over and take the square root. So when you flip over, you can write as v squared, and then on the right side you can write this one as c minus ln x to the 8, and then we take the square root. So once you take the square root, you can see v equal, you get two answers, plus or minus, because we don't know whether it's positive or negative, that depending on the initial condition. So this is x to the 8, and then we substitute v. We know that v equal y over x, so we put it there, plus or minus 1 over c minus ln x to the 8, and then multiply by x. So you can write the final answer like this. So it is plus or minus x divided by c minus ln x to the 8 square root. And if you know the initial condition, you can find which one works and also find the c. So that's how you solve the problem. So let's look at another one. This time we have this interesting one. Here we have an exponential term as well, and you can clearly see that this is homogeneous. So and we divide by xy first. We get so it divide each term, and then you can simplify this one to get this one. So you can see this simplifies to 3 e to the y of x, and in the bottom you can see it is y of x plus one y term get cancelled out, so you can get y of x again. Okay, so now we can use substitution. Then we get when you substitute, you get this one. So you get v plus v prime x on this. That's always. On the other side, now we get 3 ev over v plus v. So you can see this term get cancelled out. So you get this one as the leftovers. So if you rearrange, you can get v on this side, e to the negative v also, and the dv. And on the other side it is 3 of x. And then what you do, we integrate both sides. And you have to use integration by parts for this part, you can see. So so we can use the shortcut, the di. And if you are not familiar with the di method, you can look at that in the description. There's a link for that. So we pick the v and then negative e to the negative v, take the derivative, take the integral, take the derivative again, and integral. And then what we do, we multiply across the diagonal, starting with the plus sign and the minus sign. So we can plug in that here. So the first term is negative. So we multiply the terms across the diagonal. So we start with the first one. So we multiply these two and the next two like that. So first one is negative v e to the negative v. And the next term is again e to the negative v. That's what you get. On the other side, it is 3 ln epsilon x plus c. We call it c1 for a reason. And then you can isolate, you can factor v plus 1 and e to the minus v, and then also you can multiply by the negative sign. So it's got negative 3 ln x, and then you also get negative c1. So you can call all this negative 3 ln x just plus c. It doesn't matter, it's just a term, constant. Okay, now we can solve for y. So we can substitute for y over v. So it is y over x plus 1, and then this is e to the y of x, and then we have negative 3 ln x plus c. So this is the implicit solution of y. And if you want, you can actually simplify the right side a little bit. You can write this one as with another c, because you can write this c as ln with another c, small c. So if you write it like that, actually you can write the whole thing as ln c, small c over x cube. You can write it like that. So that's like just a little bit of simplification. It doesn't make much big difference. Okay, so let's look at the next one. So we have x squared plus y squared dx plus x squared minus y x squared minus xy dy. So this is what we normally call the linear form. We write as like a not in the normal form. And then, but we can see still, so this one is also homogeneous. When you write the normal form, this is what you get. So gonna solve for dy over dx. So you can move the terms around and divide. So when you do that, you get x squared plus y squared divided by, since you move the other side, add xy first to get the right sign. So that's what you get. That's a normal form. And you can see clearly this is homogeneous. So we can use substitution as before. Before we do that, actually you can see if you divide by x squared term, the top and bottom, you can write this one as 1 plus y over x squared, and the first term when you divide by x squared, one of the x get cancelled, so you get y over x minus 1. That's what you get, and it's clearly see that it is a function of y over x. So let's use substitution now. When you substitute these to the equation, we get this one. In previous examples, and you will see that you saw that actually it's always the v term get cancelled out. So we had that question, what happen if it is not the case? So this is a good example, what happen if you don't see it. So what we do, we're going to isolate this term. So we're going to move the v to the other side. So that means it is v prime x equal, so it is 1 plus v squared over v minus 1 minus v, and then we take the common denominator. So when you do that, you get 1 plus v squared minus v times the other factor divided by v minus 1. And then what happened now, when you distribute, you get negative v squared, and that get cancelled with the v squared term, and also get plus v. So you finally get this one. So you finally get here v plus 1 over v minus 1. Okay, and then clearly you can see that this is separable now. So separable. So we're going to use separation of arguments. So we're going to move the terms around. So we get this one after we change the variables to the two different sides, and then we can integrate. Now the question is how to integrate the left side is okay, we know that, which is ln x plus c. What we do with the right side? For what is the left side? Left side, actually we can do a nice algebra trick. You can write this one as, if you write the numerator as v plus 1 minus 2, so you can write this one as 1 minus 2 over v plus 1. We do this one many times in our partial fractions video because it's like a common trick that we do. We can try to recreate the numerator term in the denominator, actually the denominator term in the numerator, which is v plus 1, but when you want to go to plus 1, you get minus 2 to match it, and then we divide term by term. That's what you get. And on the other side we have ln x plus c, and then which is very easy to integrate. So it is v minus 2 ln v plus 1 equal ln x plus c. And then what we can do, actually we don't write a c like that, just for algebra purposes. Actually we can do that later. So let's use a substitution now. So using the substitution, so using v equal y of x, so we can write this one as y of x minus 2 ln, and then we have y of x again here plus 1. On the other side we have ln x plus c. Now what I'm going to do, I'm going to isolate the y(x) term here and bring everything else to the other side. So that means we're going to get ln 2, actually 2 times. So 2 actually you can bring it inside. So if you bring inside, you can write this one as x plus y to the x whole thing squared. We can write it like that. That's much better. And then we have plus ln x, and we also do another algebra trick. So what we can do, instead of c, we write this one as ln c using another one. So this is like uppercase, the other one is lowercase. So we can write it like that using a different, because then you can combine them. That's the whole point. Now we can actually combine all these 3 terms into one log. So we can write it like this. So combining terms, you can write this one as ln. If you combine all of them, you can see it's a c, and then we have x plus y squared, and one of the c get cancelled out. So you get only one of the x get cancelled. So you only get 1x. So that's what happened. Now what we do, we write the if you write it in exponential form, it looks better. So you get you can write this one as x plus y. If you solve for x plus y squared, and you can get x over c, in this case c, you can get x over c e to the y of x. So you can write it like that. So that is the solution is again an implicit solution for the for y. Okay. So let's look at one last problem. So let's try this one as the last one, and you can clearly see that each term has the degree 2. So this is homogeneous. And so we're gonna first divide by x squared to write in this form, and then use a substitution. We're gonna get on the left side v plus v prime x. On the other side we get v squared minus 6, and then clearly see that this is separable. So taking all the terms to one side and dividing, we can write it like this, and then dividing we have this. So integrate both sides. So on the right side you get ln x plus c as many times. Now what do you do with the left side? Left side you have to use the partial fraction method. So we can write the corresponding partial fractions like this. The denominator has factors x minus 3 and x plus 3, x plus 2. So then we can write this form, and then we can use find the a and b using the shortcut, or what we call the cover-up method. And you can see the a is 1/5, v minus 3, and then b is negative 1/5, and then v plus 2. Okay, so if you are not familiar with the cover-up method, you can find the link in the description. That's like a quick way to find these numbers when you have linear factors. Okay, so we get that. Now we can write the integral, and this is going to give you the log functions. And if you combine them into one, we can write it like this. Now we can substitute that to the equation, so we get this one. So when you multiply by 5, you get this one. Now what we do for algebra purposes, we're going to call this whole term is c. Then you can actually combine all of them into one. So it is ln, you can write this one as c x to the 5th power. And then what we can do, we can remove the log term, and we can write this one in, using the like this. We can do this because it's a one-to-one function, and but there is a plus or minus, but this c can take care of that, so we don't need to put that extra. Okay, and after that what we can do, we're going to cross multiply and solve for v first. Dividing, we get this one, and then using substitution we have, so when you multiply by x, you get this one as y. Now if you know the initial condition, you can find c. So you can try these as practice problems now. Now try these as practice problems, and if you know how to solve any of them, you can comment below. And also if you have any difficulty, you can discuss them in the comment section, and I can probably provide some feedback for that. So thank you so much for watching.